All right.
Hey,
Hello, everyone. All right, Dan, maybe you can share the slides and we get it started. Hello,
let
Paul. All our friends are here. Great.
me share my screen. Share, screen share. This guy. Share. All right.
All right, so let's get started. So welcome everyone to another OCP-TAP session. This is called number 94. Today we have Dan Biederman. And as usual, we start with introducing our speaker. Dan Biederman designs and architects network and storage ASICs and FPGAs for over 2 decades. He has worked at both large companies as well as startups. He has been working with precise time synchronization technology since 2006. At Cisco, he helped develop their first industrial precise time switch known as IE 3000. Some static we have. Welcome, Judith. Judith, can you take the microphone mute, please? All right, continuing. At Ericsson, he has continued to help with the synchronization in cellular networks. For the last 7+ years, he has worked on Intel's infrastructure processing unit known as IPU and continuing to promote precise time technologies. Dan holds a Bachelor of Engineering and Master of Engineering from Tennessee Technology University and has been granted over 30 patents worldwide. So today's talk is about precision data movement. And with no further ado, Dan, the floor is yours.
All right. Thank you, Ahmad. All right. So, hi, my name is Dan Biederman. I think most of you know me. Today I'm presenting precision data movement. There's a disclaimer here that the views of the presentation are those of Dan Biederman and not necessarily Intel. Why is it not advancing? Okay, and then there's the also legal notices and disclaimers. So the agenda today is to look back at 2022, the trends that we saw back then, and look at new precise time trends for 2024. We'll talk about AI and precision data movement, Intel style. We'll talk about chiplet precision. We'll talk about service level agreements and service level obligations, time verification, certification. We'll talk about how things are evolving and give you a conclusion and a Q&A. So precise time as a futurist. One of the things that I read and really loved was this How to Do Strategic Plannings by Amy Webb. It was from a Harvard Business Review. And it basically gives you a framework to think about how things are going to evolve in the next 1 to 2 years, which they call tactics, 2 to 5 years, which they call strategy, 5 to 10 years, which they call vision, and the system level evolution, which is beyond 10 years. And I think as precise time has gone through, a couple decades, uh, it's really nice to see, how things are evolving, but also how they will evolve. And people can plan accordingly. And so let's talk about, some of the 2002 precise time trends, right? We talked about the telecom industry and the network edge, how precise time was required by, um, the 5G infrastructure and how it was moving. We talked about how databases needed to be synchronized and how in the future, advanced database features may be based off precise time. We talked about financial transaction and how over time those financial, there was financial trading, but I think more precise time features would be evolved into those. We talked about telemetry and how it would advance to PTM. We talked about artificial intelligence and machine learning and how advanced features in those areas would come out. We talked about warehouse computing. I'm going to go ahead and advance. this slide. Oops, go back. So what we're doing now is looking at 2024 trends. There's some new things in purple that I think need to be considered and talked about, and maybe some things that we missed in 2024. One of those is this IEEE 1588 compatibility, this 802.3CX, which allows different NICs and networking equipment to use 1588 with other vendors' 1588 solutions that might have timestamping at different areas. So this is a compatibility feature of 1588 that I think is really important, to the industry, because let's say they want to use an Intel, device and a Cisco device. Those devices, if they have this 802.3CX compatibility, they'll be able to work better together. Also at the very bottom, the PFM, that was the precision frequency measurement that Julian gave, several talks ago, that I think is something that I think will become prominent and used more and more with PTM. Additionally, there's the 1588 precise time verification and PTM precision verification. I think those things will be needed to certify or need to be certified so that service level obligations and service level agreements can be made based on the verification of precise time at those locations. There's precision data movement, which is towards the center, which is what most of this talk will be about today, which is about having the right data at the right place at the right time. And this is using things like RDMA, NVMe, APIs, things that are predominant in the data center today, and how they can use precise time to get data moved around the data center. And we'll talk about time-aware GPIO and potentially how it may advance into an advanced time-aware GPIO. And we'll talk about inter-chiplet precision and, go on with that. So the first thing I'd like to talk about is precise time and artificial intelligence and machine learning. And, over the last, several decades, AI has evolved. My graduate thesis for my master's degree used AI, and that was many, many years ago. But today, one of the problems that has been brought to my attention is that the effective T-flop utilization for most AI solutions is around 46 to 57%. So, when you think about evolution, you think about, how man evolved, right? The man's brain did not, or the human brain did not evolve and double every generation. My brain's not twice as big as my mom and dad's brain, and 4 times as big as my grandparents' brain, right? But as people evolve, we've become more flexible, right? We're better optimized for our environments, and thus, we didn't need to double our brains every, generation. Processors evolved similarly, right? Originally, they may have doubled the frequency, but over time, they went to multi-core and virtualization. And now a lot of the chips are going to chiplets. And so, people need to, think smarter about how AI will evolve and, ask important questions, right? If I use today's technology, but I can somehow increase utilization, maybe I double it, right? That would be very beneficial. There's power savings, there's cost savings, there's footprint savings, and potentially, if we could go from 46 to 92%, maybe you could double the performance. What if AI changes? Am I flexible to meet those changes? The models that we use today for AI, they change. If they change in a way that makes my, accelerator not work, or my GPU not work as efficiently, then, you know, then I have to come up with a new solution. There could be underutilized resources that, you know, we can't take advantage of. And, you know, a lot of times there's wasted engineering resources to develop accelerators or to develop, you know, things that, you know, need to have a special purpose. So one of the things that I've seen a lot in literature lately is, you know, domain specialized large language models, you know, tuned to a specific task, you know, an AI CPU or different companies have different thoughts on this, right? VMware is talking about AI without GPUs. Hugging Face is talking smaller is better. Maybe these gigantic large language models, you know, we can do something better. Um, you know, talking of Tom's Hardware talks about how NVIDIA clients, you know, switched to, or an NVIDIA client switched to Intel CPUs because they could get the performance they needed and the hardware was available. And even Microsoft is talking about forming advanced AI teams for small language models. So we need to think smarter about how we do AI. So let's go back to precise time. So at Intel, we look at precise time and multiple. Hello, is there a question? Okay. They talk about AI in multiple directions, right? Or multiple dimensions, sorry. We have, in one direction, we talk about time-sensitive networking. You know, with time sync, that's like IEEE 1588. And we have a timeliness, which is like deterministic networking. And for time coordinated computing, we're talking about, for time sync, this is PTM. And for timeliness, this is doing things in real time. And so these are concepts that we need to consider and think about, you know, how could these be applied to artificial intelligence and other applications? And one of the really nice things about TCC and TSN is, you know, with precise time at the CPU, we've taken it to the last inch, right? We've taken it to the CPU. We can now have applications that run on that CPU that can use that precise time. And, you know, today with PTM, maybe we're getting tens of nanoseconds, but similar to IEEE 1588, over time, we're going to beat down that precision. And, you know, potentially there would be a white rabbit over PCIe using PTM. And when we take advantage of precise time, we'll see amazing benefits. Like, for example, you know, Meta published a paper about their window of uncertainty. When they used PTP, they were able to see 100x performance benefit with that window of uncertainty. And I think as we move closer to the CPU with TCC and TSN with 1588 precise time, you know, data centers and the applications that run on them are going to see these kinds of improvements. You know, it might not be every application, it may not be the full applications, but portions of that application. They'll be able to squeeze out 10 to 1,000 times performance benefits. And with precise time at the CPU everywhere, 5 decades, you know, of working around not being synchronized, you know, can be removed. 5 decades of, you know, band-aids and hacks, you know, can make things simpler and, you know, work much, much better. So let's apply this, you know, thinking about computing and thinking about energy. So Nikos Harvelis, you know, has a really nice paper about the rise and fall of dark silicon. And it's a great example, even though it's 28 nanometer. It gives different energy levels, right? It gives the energy level of arithmetic operation as 0.5 picojoules, as a 64-bit floating point operation at 20 picojoules, an L1 cache read as 50 picojoules, and L2, let's say 10 millimeters away, would be 356 picojoules. An L3 cache across the die is 1,100 picojoules. And if you go off chip and do a DRAM access, it's very wasteful in terms of energy, right? It's 16,000 picojoules. And so, you know, if you were to compare putting data in your L1 versus DRAM, you're looking at 3,000x performance benefit or energy benefit. And even if you went from DRAM to L3, you're going to get a 15x energy benefit. And now these ratios are for 25 nanometers, but there's similar ratios for, the most recent processes with, 3, 5, 7 nanometers, 18A. And on-chip, energy use could be reduced if we had the right data at the right place at the right time. And so this is where what I call precision data movement comes in. And it basically uses all of the TCC, the TSN all together. So precision data, or so regular data movement occurs when you're sending one data from one CPU or application to another CPU or application. This could be a storage device, it could be a server, it could be anything in the data center. And CPU applications, they use protocols like APIs and RDMA and NVMe to push that data into the host memory. And so if we look at this and we have a goal that we're going to significantly increase the T-flop utilization by using precise time and pacing techniques, now all of a sudden, things get really, really interesting. So Intel has a technology, and it's called or data direct IO, or DDIO. There are other companies that have similar protocols, but let's talk about direct data IO, DDIO. So what this allows is it allows you to save data in the cache, the L3 specifically, saving power and latency. And there's a link at the bottom if you want to go to a data brief on the Intel website and learn more about DDIO. But the good thing about this is if the NIC places things in that DDIO, it reduces the risk of a cache miss, which can add to latency and power consumption, as we talked about earlier. So one of the problems, though, is that the data coming into the NIC can be quite bursty. And hence, if we push all the data from the NIC directly into the DDIO, then the rate of input into that area won't equal the rate of consumption. And hence, you'll get things moving, getting kicked out of the cache and into the host memory. And so if we can keep things in that host memory, we can save that power, energy, and latency. We can do better. So by pacing it, we can pace it at the rate of consumption, or pace it at a rate to match the rate of consumption. And this might be ping pong buffers, or maybe it's dividing the DDIO area up into 3 areas, where one area is I'm loading the data right now. The next area I'm consuming the data, and the next area is I'm clearing that data out, whether it's pushing it back across the NIC, it's pushing it to the host memory to be used later. There are other important cool things in Intel processors that are really helpful here, and that's cache QoS. So what this does is it allows you to lock certain areas of the cache so they won't get evicted. So if you're doing something that has submission queues or completion queues, has head and tail pointers, those areas could be used and protected by Intel Cache QoS. And so now that you have this technology and you can take advantage of it, you can keep things in the cache and take advantage of that processing. Is there a question? Okay, and I will continue. So let's go back to applying this to AI and LLM, artificial intelligence and machine learning models. So the CPU cache is relatively small. It's not going to hold trillions of parameters. It's not going to hold billions of parameters unless they're like single bit or something like that. So going back to the evolution, we need to think smarter about how we do AI. And this means, maybe we break up the AI into smaller chunks that can fit into the cache, or the DDIO sections that can be processed faster and processed with significantly lower power. And using the DDIO and cache QoS or the similar things that the processor you're using has, you can get the precise data, at the precise time, and the precise place to take advantage of it. So let's think about how this might influence next generation data center architecture. So at Open Compute, they have the Xeon EX architecture, right? At the top, you see there's 4 CPUs that are connected to NICs, and then you have the next layer, the CC, that has the RDMA and NVMe kind of interfaces and has PCIe switches. And then the EP has the accelerator modules, the OAMs, the Open Compute accelerator modules, right? So the cool thing about this is we can put accelerator modules there that are special purpose and get great performance out of them. The negative thing about that is that hardware, all of that hardware can only be used for that special purpose. And so, in the future architectures, those open accelerator modules may be using AI CPUs or general purpose CPUs that have accelerators for AI on them. And when things are synchronized with PTM and 1588, all of a sudden, you can take advantage of the things that we've talked about earlier today and get precision data movement. And so, why are we thinking about replacing those, accelerator modules, their GPUs or whatever are going there with synchronized AI CPUs? Well, one is flexibility. If a Xeon server can do 10 billion large language models in less than, say, 50 milliseconds, then maybe you could potentially scale it, over a data center rack to do 100 billion large language or parameter large language model. Maybe you could go over a pod and do 1 trillion, parameters. And the great thing about having a server there is they're general purpose. So let's say today my workload is AI intensive. I need to get that AI. But then tomorrow I need to use databases, and then in the future, maybe I'm doing a microservice solution or a video solution, or maybe I have a big data Hadoop type solution, right? With something that's specialized with specialized hardware there, you don't get the advantage of the flexibility of a general purpose server. And what this might end up looking like is some sort of software defined rack or pod or warehouse computer, where software defines over time what this does. And it could mean that right now that rack is working on a 10 billion parameter large language model, but 50 milliseconds from now, it could be processing a database. And 100 milliseconds after, processing the large language model, it could be doing some sort of vector processing. And 150 milliseconds later, it could be doing some video load or some big data Hadoop thing. And so, replacing these accelerators with, Hisham, I think your microphone is on. If you replace these open accelerator models, or modules with, servers, whether it's, whichever company you use, you now have the flexibility to do many different things, not just AI. So let's stop and let's talk about precise time and chiplets. And so what are chiplets? Well, you can have multiple small ASICs that you combine together into a single SoC. In the past, everything was monolithic. We had one die that did everything. But now, and in the future, we're moving more towards doing a chiplet-based solution. And what a NIC chiplet-based solution might look like, or even a server, is you would have potentially Ethernet chiplets talking to the Ethernet interface. And those could be updated over time as the Ethernet standards update over time. You could have a networking chiplet, which does all your switching and all your lookups. You know, at the top, you could have one or more PCIe chiplets that talk to disks or your servers or SSDs or GPUs. You could have an AI chiplet that is used in coordination with all the other chiplets. You could have a compute chiplet, and you could have memory chiplets or even devices that hang off that, like memory interfaces, like DDR. So all of these things have to work together, and they have to uh, potentially pass time. And the one cool thing about going to this chiplet methodology is, you know, let's say you want to use, you know, an Intel compute server, but you want to use an AMD or, you know, an NVIDIA AI chiplet, or you want to use networking silicon from, say, Cisco, or you want to use, you know, today's Ethernet technology from one vendor, but tomorrow's Ethernet technology from a different vendor. This allows, having a chiplet technology allows people to interact with other vendors' chips and create an amazing solution. But we also, when we do this, we need to think about time synchronization and how that multi-vendor SoC will pass time, right? So, you know, one of the easiest ways that you can pass time, and it's been used by industry on connecting multiple devices, is to use something like a clock or a pulse per second. And, you know, you could get 1588 time off of, say, Ethernet chiplet 1. You could pass it to a buffer and then pass it to everybody else. The PCIe could then, you know, coordinate with PTM across its interface to whatever it's connected to. And this is, you know, works great. If it was my, you know, you know, but you know, what happens if that second Ethernet chiplet now is the the grandmaster or the leader of this precise time? If that's the case, then if I made it so only chiplet 1 could drive it, we're in trouble, right? So now we need to have chiplet 2 be able to drive it. Or what if we want to have a PTM centric solution where one of the PCIe chiplets needs to drive it? Or maybe the networking chiplet needs to drive it. So we need to think about these kind of things. You know, one thing you could think about is, well, maybe we could have some sort of ring that passes time around. And, you know, and every second, everyone passes their time around from one chiplet to another. Or maybe we have a clock that's passed from one chiplet to another. And, you know, a lot of, you know, ways that this could be done is if we had time aware GPIO pins that could pass time. And so, you know, this is great, but what if all of a sudden we're like, oh, we need to power down our AI chiplet? All right, well, we have a ring that went around. Well, now it's going in one direction. The AI chiplet, if it went from, say, Ethernet chiplet 1 all the way, you know, in a circle around to Ethernet chiplet 2, taking out the AI chiplet would mean that the compute, the memory, and the Ethernet chiplet 2 are now off of this. One thing that's cool about time-aware GPIO is it tends to be bidirectional. So if we had a time-aware GPIO that was bidirectional, we could turn the ring from Ethernet chiplet 1 to Ethernet chiplet 2 to memory to compute. And then that way we could pass time, you know, clockwise going one direction, counterclockwise going the other direction. So another thing we could do, you know, to handle this kind of issue would be to have dual rings. We could have two defined rings that one going one direction, one going the other direction. We could have one verify the other. We could have potentially less jitter or latency and allow neighboring chiplets to power off. And we wouldn't have that problem. And as I mentioned earlier, you could always flip the direction of the time-aware GPIO if that's required. We could also have PTM between chiplets, right? It's a little bit more signals than, say, a pulse or clock, but it's already a technology that's out there and that we can use. And if we have a standard like UCIe, we could put PTM over that standard. If I was developing the chip myself with all the chiplets I'm talking to are from my company, a proprietary standard makes sense. But in the future, if I want to use someone else's silicon, whether it be a competitor or, a customer, then we need to think about uh, how we're going to communicate time with chiplets. So, one thing we need to think about is how to get every vendor to do it the same way. In the past, if you have an Ethernet device, it has to comply to an Ethernet standard. We need to do something similar, but where should this occur, right? Maybe this should occur at the IETF, maybe this should occur in the IEEE, maybe it should occur here at, OCP-TAP. But we should definitely talk about it and try and get an understanding of where we want and what direction we want this to go. So let's talk about certification of precise time. So currently in a lot of data center applications, or if you're a cloud service provider, you sell things based off of a service level agreement or service level obligation. You agree that one of the common things is that the uptime of the server will reach 99.999% or 5 nines, that the server will be up for, that percentage of time. So we need, I think, as precise time becomes more prevalent in the data center, we'll need a way to certify and verify it, because if the applications can get really good benefits from it, then why would I want to go with a service provider who cannot provide me, certification or verification that the precise time was available everywhere that I was using it in a distributed system? And so, um, you know, one statement a data center or a cloud service provider may make is that, hey, all of the devices within, this distributed database that you're running is within 100 nanoseconds of each other. How do we know this? How do we verify this? And down to what level, right? Is it just at the NIC? Is it, just in a rack? Is it across a warehouse computer? Is it down to the chiplet? Um, my belief is it'll be everywhere in those places. And in fact, it may be across geos as well, is that we have to certify that the precise time across geos, different geographically located data centers, has the same precise time. And there may be audits that, hey, you said that you're giving me the service level agreement. My application is running poorly on it. Tell me if the reason it's running is because your precise time is not meeting the SLA, this 100 nanoseconds that we said it would be. And so, why, one of the things you might ask is, well, why will applications care about precise time? Well, if they run better, if they have faster commits, if they can mitigate decisions or conflicts much faster, if they need to have a consistent view of time, and to reduce the number of hacks that people have put in over time to make asynchronous distributed computing work. And so, and it might also be that telecom applications by design, if we want to run them in a cloud service provider, they may require, I have this class D requirement, 5 nanoseconds requirement, right? Now that's to the endpoint, but it might be that from the application to, the data center application to the end device may have a requirement, and class D may just be a portion of it. We talked about service level agreements and obligations. Customers will want precision to be verifiable, that all the servers in my warehouse computer, my cluster of computers that I'm running this application on, are within, 100 nanoseconds, 25 nanoseconds, a microsecond. And as a cloud service provider, we probably will want to track, are we or are we going outside of the precision that we're obligated to give? And if we're about to lose that precision, if we have servers or equipment that's drifting away from it, have alerts that say, hey, this guy is almost out of the precision. And let's migrate that machine or those machines to other servers that have 1588 or PTM precision meeting the requirements of my service level obligation. And so let's talk about time-aware GPIO. This is one way which I think we may be able to do certification. It's in, some Intel products today. I think it'll be in a lot more in the future, and I think it'll be in a lot more competitors' products in the future. In the past, people have been more interested in time-aware GPIO than, PTM, getting precise time to the processor. And I think that certification is the reason that is. There's Linux driver for, Intel for doing PPS out today that's available across the time-aware GPIO. But we can do so much more with time-aware GPIO. And I think in the future, we should look at, standardizing it or making recommendations on, hey, this is where we want time-aware GPIO to go. Maybe we pulse per second, just doesn't cut it, right? We want to do other amazing things with it. And we want to enhance it. But where should we have these discussions? Where should they be standardized? Is this an IETF thing, an IEEE thing, an OCP-TAP thing? I think we need to consider where we're going to do this. And so I wanted to give a couple updates since the 2022 presentation on things that I found were amazing. One of the things is, consider latency. I presented this back in 2022 and, talked about, how Intel was doing things to reduce latency. We talked about, how other customers were saying that they were being attacked by killer microseconds, right? That their applications cannot handle, as we add more and more microsecond latency for things. We talked about how FEC killed the cut-through switch. And, one of the great things that I saw in the last 2 years was Arista killed the FEC. So using Arista products, you could potentially get rid of that latency associated with the FEC. And I'm really, really happy to see that people are looking at these things. Another thing that we talked about was how you could use precise time for scheduling and using it for semaphores and pacing. And talked about how Intel had a transport library for SMPTE ST2110. And that has now been open sourced. And there's a link at the end where you can actually go and use these libraries that Intel developed and now other people are developing on in an open source fashion. So let's talk about next steps. So, the same as the last presentation, the slide is very similar, is, we're on a mission to make data center computing performance much better, or computing performance in general much better. And you can help with this mission, right? You can present your precise times use cases and data to the OCP-TAP so others can learn and reference them. You can share your use cases and data directly with Intel, if and other vendors directly, so that can be analyzed, and if appropriately, implementations can be built around it to make them run faster. Neither OCP-TAP or Intel or any other vendor, can fix a problem if we can't see it and understand it. The other thing is you can ask questions. Are there inefficiencies from being, proactive versus being, reactive. Can there be bottlenecks, or are there bottlenecks that can be reduced or removed if you have precise time synchronization? Similar to the previous slide where I showed, pacing of the data or pacing of operations. If we can have things better paced, any shared resource, whether it be bandwidth or, a compute resource, can be better, optimized for better performance. And are there proof of concepts that we can do that are relatively easy to get the data? And let's look at some of those ideas, let's talk about them. So one thing that Ahmad and I had talked about previously is how could we get academia involved? Academia does a lot of great research, and often they're senior projects that students have to research. They need to go out and find out where these projects are, or what project am I going to work on so that I can graduate. Similarly, masters and PhDs have thesis. These theses are things that try to, expand the scope of knowledge of the human race and document these so that other people can use them, publish papers on them. And if we had a list of projects, like precision data movement, what's the best way to implement that precision data movement? If I have all these features that Dan's talking about today, let's see what is the right size of the AI. Could I model the AI around, a more general purpose application so that I can use that application for databases and big data and microservices? This group here has a lot of knowledge that we could share with the academic community and with students looking for these world-changing projects. We could make a collection of, 10, 20 projects and, share them with any university in the world that wants to participate, right? And have a chance to have their students advance time-related projects. Remove these 5 decades of band-aids and hacks. Remove these, these things that cause, bottlenecks and performance issues in our applications. Make it so that we can better do AI and precision data movement. And we're a data-driven society. If we can see that there are benefits from these improvements, then let's do it. Let's get the data, on, how to move applications to precise time. Thinking of Jerry Maguire, show me the data, right? Dan can talk all he wants, but if we have actual data and we can actually see that, hey, they did this, they removed this 50-year-old hack and they were able to get amazing performance benefits, then let's do it. Let's talk about new ways to use precise time and make applications and the data center itself run better. So if I have a final message today, and it's going to be about getting precise time everywhere. All servers and all applications of data center should have and use precise time today. As the applications mature and we get more and more eyes looking at ways to make these applications work better in a precise time environment, we don't want to go back and say, oh man, back in 2024, I didn't think about how I could get precise time to my server. We need to think about that now. So, 2 years down the road, it's like, oh, we can run 10 times faster, but we have to replace our data center because we didn't think about it 2 years ago. I think these are things that we, as OCP-TAP need to think about. So in conclusion, I hope you enjoyed the story, the applications, the learning, that happened today. I hope you learned about, trends in precise time, talked about precision data movement, talked about chiplets. We talked about, AI as an application and how it could use things like DDIO and cache QoS, not only from, say, Intel servers, but from other companies that have similar technology, and talked about the certification of time. And also, we talked, about ideas for the future. And, it leaves me with a final question. What wonderful thing can you do with precise time? So I've listed some resources here. You're welcome to look at these. The first one talks about, precise time adapters using 1588 at Intel. There's a link here to the media transport library that's been open sourced. And thank you. Any questions?
Thank you, Dan. Yeah, let's open the floor for questions.
Let me stop sharing.
All right,
Any
maybe
questions?
maybe I can start with the icebreaker question. So,
Okay.
can you also share with us more than, let's say, what you will get benefits from precise time when it comes to data path and everything, all of these things? Anything beyond that, let's say for power consumption, for all of these other things? So,
Well, I think, like I tried to explain, if you think about where the data is going and in what direction and how it's being used, if you can move the data so that it's always in the cache. And, I think the technology there today, at least in Intel, is there at, the L3 cache. But if we could get it right down to the unit, whether it's an accelerator or whatever, that has the precise time, I think the benefits, could be it was 300x performance and benefit if you could get it down right next to the processing unit versus going out to, say, a DDR memory, right? And so if you could do that, then you're saving, 300x power for that data because it went directly to the processing unit as opposed to going to an external memory. And so,
all
Could I
right.
ask a kind of follow-on question from that?
sure.
So in order to get time at those really embedded levels in the CPUs and things like that, it seems like you need really, really small clocks. Is that the case, or are there better ways to, clock a CPU or get time at those levels than needing
So-
kind of like a little tiny chip?
Right. So there are lots of things when you have to consider, right, precise time when it's a CPU, right? If it's an out of order instruction CPU, right, that CPU may have problems with precise time down to, say, a nanosecond, right? If I can have 150 instructions that are being processed out of order, and I operate on, say, one per nanosecond, right? You may have some problems there with regards to precise time down to that level. But if you're doing things always in order, like you have a data stream that's in a FIFO order, you could take advantage of it. There are also uncertainties with regards to the timekeeping of the CPU, right? So even though we have precise time at the CPU, and ideally, we'd love to get it to the, say, sub-nanosecond level, that's not possible with the current implementations that I'm aware of. Basically, we may have an ART timer that has, a 5 nanosecond, 10 nanosecond, 25 nanosecond base time. And this timer may be associated with instructions, or that can be accessed by the instructions. And so there may be, hiccups, in the current generation, but it doesn't mean in the future generation that we will find ways to make it more precise down to the CPU and the CPU instruction. I think the last time I talked about an instruction called T-pause, right, which is an instruction that Intel has that basically pauses until a precise time. And that precise time is based off of the timekeeping of that Xeon processor. And it's possible that it could be off by, tens of nanoseconds or something like that. So it's precise time compared to, say, NP or NTP, but it's not precise time compared to White Rabbit or, down to the nanosecond level. Does that answer your question?
Yeah, I think it does. Would you have anything more to say about kind of where you potentially see White Rabbit implementations going for some of these data center architectures?
I think the I think with regards to 1588, White Rabbit is, something to be considered if the cost is acceptable. And I think getting it, down to the CPU, if we can get the applications where, hey, we can get so much performance benefit from it, then we'll drive it. But I don't see like White Rabbit precision getting down to the CPU unless you're in some sort of like FPGA architecture or something like that, where you can actually go in and have PTM and manipulate it, right to the processor. Like some Intel FPGAs allow you to add instructions and stuff like that into the processor cores. So if you wanted to actually get an instruction that was very precise, or had instructions work on precise time, that would be something that would have to go in the FPGA logic outside of the instruction core. But it's doable. It's things that I think will eventually happen. But right now at Xeon, I think read TSC and TPAWS are pretty much those type of instructions is all we'll get, in the current generation.
Thank you so much. I really appreciate you taking time to answer those questions.
No problem. Another question?
I have a question.
Yes.
So how do you compare between a system which is synchronous using time synchronization protocols, BTB or whatever, a synchronous system which is event driven?
How would you synchronize those
No,
two things?
how do you compare between them? There are two architectures. One is synchronous system using time synchronization, and another one which is asynchronous, which is event driven. In your case, how you compare between these two?
I haven't thought about it in that way in a long time. I think I'm not sure I have a good answer for that. I mean, if you had a synchronous system that was doing a database, right, then everything in that database is synchronous, and you don't need the asynchronous, conflict mitigation and stuff like that, versus a synchronized distributed system that runs a database asynchronously, right? I mean, I think the ultimate goal would be to try and move the synchronized distributed system, that's running on top of an asynchronous network over to a synchronous system. I think that, one of the things, in distributed systems that we'll need to do is pace traffic. We'll need to, add, congestion control, better congestion control, one-way congestion control, so that we know how to get data from, different nodes in an asynchronous system, allowing it to work like a synchronous system. Does that answer your question? It's kind of a tough question.
I'll just throw in real quick.
We can talk about it offline, actually.
Okay, all right. Yeah, I'd love to hear more about your thoughts on this,
Yeah.
and understand it a little bit more. I haven't given it as much thought as to give a great answer.
Do you have an email address?
It's on this at the beginning,
Okay.
dan.biederman@intel.com.
We
Okay,
have
thank you.
Bob, his hands up. Let's see what Bob's question is. Bob, go ahead.
Yeah, thanks, Ahmad. And thanks, Dan. Great presentation. Just a quick
Mhm.
quick question on the UCIe mention, the chiplet problem. Being involved there and not trying to overshare what that group is working with, I'm aware of Peter and Gerald's work in the compliance group there. And I was just curious if you've presented in some space with UCIe on your timing needs as they start to look at test and validation, because I, from the University of New Hampshire here, I have a very strong interest in seeing TSN and verification of timing, be it PTM, PTP, White Rabbit, or UCIe level.
Right. I have not talked to them directly or presented to them directly. If you want to give an introductory email, between myself and them, that would be great.
Happy to. Thank you for the talk again.
Bijan, you wanted to say something?
No.
All right. Anybody else? Any other questions?
Right.
All right. Well, I'd like to thank everyone for coming. Hopefully you learned stuff. Or is there a question?
Sorry, the
Okay.
OCP college, I was interested in that. And can you elaborate on that?
Oh, so in other words, if we were to do college projects and stuff like that, is that what you're asking?
What's your vision?
I think the vision is open right now.
Okay.
I think the goal is to, get college students excited about this, excited that they can have an impact. And then the goal is to get data. So often, people are like, precise time is great. I can see it used in telecom, but, I can't see it used in database. Well, if we had, 20 college students that are working on theses and senior projects in the database area, they may come out with, oh my goodness, we were able to reduce conflict mitigation by this amount, improving performance by that amount. That to me would be great data, right? And I think, for the college students, it would be good because, maybe we have them present at OCP-TAP meetings or have special, college presentations where they present 15 minutes to, all the different data centers. And people can say, oh, wow, I could use this in my cloud service provider, or we really need a guy like that to help us. I'm really interested in learning more about his work, and maybe he can bring that to my company. So I think it's kind of a win-win situation for both, the industry and the companies that are running it, as well as for the college students trying to expand human knowledge and, trying to do something that, will help them get a job in this field. Does that make sense?
Yeah. That sounds really great. Thank you.
Right. Any more questions? Not hearing none. We'll adjourn and we'll see you guys in 2 weeks.
Right. Thanks, everyone.
Thank you, Dan. Thank you,
Thanks,
everyone.
Dan.
Thank you.
Bye,
Bye-bye.
everyone.
Thank you.
Thank you.